It's my pleasure to start this session on Azure Autonomy. Our next speaker is Samuel Coogan. He's an assistant professor at Georgia Tech with a joint appointment in the School of Electrical and Computer Engineering and the School of Civil and Environmental Engineering. His research is in the area of dynamical system and autonomy. And the title of the talk is Efficient Reachability for Safe Autonomous System and Mixed Monotone Approach. So please, Professor Coogan, listener is yours.
Yeah, great. Thank you for the introduction, and thanks a lot for the invitation to be part of this conference. I've really enjoyed the talks, and it's an honor to be joining such a nice group of speakers. So let me tell you a little bit about broadly what my research group does at Georgia Tech. So we call ourselves the Formal Methods and Autonomous Control of Transportation Systems Lab. So my background is control theory. Broadly speaking, we apply controls and control theory to problems in autonomous systems. We're typically motivated by the application domain of transportation, but the work we do tends to be more on the theoretical side. So, for example, we apply our tools to multi-agent distributed control problems, to analysis and control of flow networks, problems in formal methods and control systems. And then the focus of today's talk is largely going to be in the space of safe autonomy. How can we ensure that these autonomous systems, possibly controlled by complex controllers, operate safely, even without a priori verified control strategies? So that's going to be the focus of today's talk. So I'm going to spend the first few slides easing into a familiar notion if you're a control theorist, something that may be a little bit less familiar if you're not, this concept of the reachable set of a dynamical system. So it's going to get a little technical, but I'm going to try to keep it simple with some figures. So suppose you have a dynamical system, which for my purposes will be an ordinary differential equation with a state vector x, time derivative defined by a vector field f. This vector field is possibly perturbed by an unknown disturbance vector w. So the reachable set, informally, it characterizes the possible evolution of the system over time. So for example, say you have an initial set of states, you choose a particular point in that initial set, x1, you simulate the system forward under some disturbance, right? Or you compute the system under some disturbance, and you arrive, say, at points x1 at time t. So this is part of the reachable set for this system at time t. So if I did this, say, for the same initial conditions, it's possible I end up at a different final state, say x1 prime. This is because in this particular instantiation, we have a disturbance vector w. So a different disturbance will cause a different endpoint of our trajectory. And of course, if I choose a different initial condition like x2, I'll end up at a different endpoint, x2 at time t, right? So I can, in principle, do this kind of analysis for a whole bunch of initial points. I can get a whole bunch of final points. And if I did this for every possible initial point in, say, some initial sets, I would get some potentially strange looking shape. And I could call this in this case, the T reachable set for the system, because this is the reachable set over a time horizon T. It's generally a rule of thumb in systems, in dynamical systems theory and control theory, that it's difficult to grapple and get a hand on this reachable set precisely. So typically, we're interested in somehow approximating this reachable set. For purposes of safety properties and reachability properties, a lot of times what you want is an overapproximation of this reachable set. So for example, here is an ellipsoidal overapproximation of this reachable set. So now suppose you had, say, an unsafe set of the state space, and you wanted to check and make sure that your system didn't intersect this unsafe set over this horizon t for this set of initial conditions. I can use this overapproximation as a sufficient condition. If the overapproximation doesn't intersect the unsafe set, then I know that the real reachable set doesn't intersect the unsafe set. Likewise, if I have a target goal region I'm trying to reach, I can make sure that the overapproximation is fully contained within this target set. And I know, therefore, that the actual reachable set is fully contained within this target set. So generally speaking, depending on the application of interest, but in the applications in this talk, we're going to be interested in obtaining these over approximations of reachable sets. So there's a growing need for the ability to compute reachable sets in different contexts very quickly. So speed is becoming an increasingly important topic in the realm of reachability theory. And I like to divide the need for speed in sort of two different camps, at least for the research that we think about in my group. So on the left, the reason you might be interested in these fast reachability methods is for formal methods contexts. So in the realm of formal methods, a common method for computing formally correct control strategies or verifying formally some control strategies is to partition a dynamical system state space into a finite number of regions and then try to reason about the possible evolution from each of these finite regions. What this means is one has to compute reachable sets from each of these finite regions. And so you have a large number of reachable set computations that need to happen, possibly millions of them. And so there's you need to have very fast computations for these reachable sets in order to be able to compute formally these controllers or verify these controllers. The other large application that we're going to focus on in this talk is this idea of safe autonomy, where we embed reachable set computations in the control loop to somehow reason about the possible future evolution of the system and then make changes, perhaps in real time in the control loop. And so that's going to be what we focus on today in this talk. We have quite a bit of work on this first problem in the formal methods world, but I largely won't touch on that at all in this talk. So what are we doing in this talk? So the challenge we're addressing is that reachability methods for nonlinear systems generally are computationally expensive, therefore slow to compute. What we're going to do today is we're going to answer three questions. Is there a class of nonlinear systems where we can pose efficient reachable set computations? And what we'll see is that there's a class of systems that we call mixed monotone systems. That's a fairly general class for which we can efficiently compute over approximations of reachable sets. What I'll do next is I'll show how we can use the properties of mixed monotonicity to do just that, compute reachable sets, compute something very closely related to reachable sets, so-called invariant sets. And we'll see that we can do that by embedding this system into a higher dimensional system where we just compute single trajectories in this higher dimensional system. And at the end of the talk, I'm going to show how we can use these ideas to guarantee safe autonomy within the loop reachability. And we're going to use a little bit of control barrier function theory to make that happen. But really the crux of the novelty will come from applying the mixed monotone systems theory. Good. So let me very briefly review the more classical notion of monotone systems. So a dynamical system, x dot equals f of x comma w, just like the system we had when we started with talking about reachable sets. We're going to consider this system, and we're going to restrict, just for some technical ease, to the case where the state space calligraphic x and the disturbance space calligraphic w are hyperrectangles or higher dimensional boxes. We'll use the notation phi to denote the state transition map for this system when we have an initial state x naught and some disturbance signal boldface w that maps time to our possible set of disturbances. And the definition of monotonicity is as follows. If you take an ordered pair of initial conditions, say x naught and x naught prime, so x naught less than or equal to x naught prime, here the less than equal to for two vectors means that every entries of the vectors satisfy this less than or equal to relationship. And if you take an ordered pair of disturbance signals, so that w of t is less than or equal to w prime of t for all t, then it holds that the state transition map also remains ordered for all time. So simply put, monotone systems maintain partial orders on states as the system evolves under partial ordered disturbance inputs. So throughout this talk, if I write less than or equal to or greater than or equal to without some sort of subscript, I'm talking about the standard canonical ordering where we look at the entry-wise orderings and the vectors. But you can generalize the idea of monotone systems theory to arbitrary cones, and we will do that in one particular special case later in the talk. Good. So that's the definition of monotone systems theory. There's an equivalent way of characterizing monotonicity in terms of the Jacobian matrix for the vector field for the system. So that condition is as follows. An equivalent infinitesimal characterization, the system is monotone if and only if each of the off-diagonal entries of the Jacobian matrix, partial of f with respect to x, is non-negative for all states x and all states w, or all disturbances w. And again, this just has to hold off that diagonal. And then the second condition is that the Jacobian matrix with respect to the disturbance input is always positive for all entries. And monotonicity is an old property of dynamical systems. It's been studied in a number of domains. It's well known to provide a suite of control theoretic tools useful for example, studying equilibria, their convergence, and their reachability. There's a few canonical papers covering these topics, and a number of researchers that have made important contributions to this area recently and in the recent past. So a generalization of the notion of monotonicity that we're focusing on in this talk is this concept of mixed monotonicity. So here's the definition of mixed monotonicity. So we say a system is mixed monotone with respect to a certain decomposition function d if the following properties hold. So first, notice that this decomposition function takes 4 arguments. It takes 2 state-like arguments, x and x, and it takes 2 disturbance-like arguments in w and w. And it needs to satisfy these properties. The first is that if I substitute in the same value for the pair of the states x and x, and the same value for the pair of disturbance inputs w and w into the decomposition function, I recover my original vector field f. So this tells you that the decomposition function somehow contains all of the information that was originally in the vector field f. And then it needs to satisfy these other ordering properties that are reminiscent of the infinitesimal characterization of monotonicity. So the second property is that the partial derivative of each of the ith entry of the decomposition function with respect to the jth entry of the first state argument needs to be positive for all ij. This is just like in the monotone, all I not equal to j. This is just like the condition in the monotone systems case. The third condition is that if I take this derivative with respect to the second state argument, which we'll denote with hatted variables x hat, this needs to be non-positive, this time for all ij. And then we also need to have an ordering relationship with respect to the disturbance inputs w and w hat. So we need the partial derivatives of di with respect to wk to be positive, and the partial derivatives of di with respect to w hat k to be non-positive for all ik. And these conditions generalize the idea of monotone systems theory to allow for both increasing and decreasing components in the vector field f. And the decomposition function d captures all of these effects through these coupled arguments. So 2 natural questions arise when you see this definition. The first question is, how general is this characterization? Or do many systems satisfy this characterization? Do very few systems satisfy this characterization? It's going to turn out that this definition is actually very general, but its usefulness really depends on the choice of d. So a system might have multiple decomposition functions. In general, it does have multiple decomposition functions, and some are better than others. The second question that comes up is, how can we use these ideas for reachability and safety? And we're going to see that something called the monotone embedding system plays an important role here. So that's what we'll do the next few slides of this talk. So let me begin just by kind of giving a very simple example to demonstrate the power of the mixed monotone systems theory. In a lot of ways, this is I consider this to be a bit of a canonical example for reasons that I'll try to explain as we go along. So this is the general Lotka-Volterra model. It models cooperating and competing species in some ecosystem. And so the equations are that the rate of change of the ith population is somehow proportional to the product of the current population and some linear combination of the other populations. And these coefficients, Cij, can be either positive or negative. If they're positive, they capture a cooperative effect between the 2 species. And if it's negative, it captures a competitive effect between the 2 species. And so very naturally, there's these cooperative and competing effects in the dynamics, and the decomposition function one would construct for the system decomposes these cooperative and these competing effects. So in particular, the decomposition function you obtain for this system looks like the following. First, you pull out the ith components of the dynamics. These are isolated to just the ith species. And then for the remaining species, you divide them into 2 parts. You look at those species that have cooperative effects for the ith species, and you use the Cij variable here, and in the event that Cij is negative, you then associate it with the hatted variable x hat j, and this becomes a valid decomposition function for this system that does exactly what the definition of mixed monotonicity seeks out to do: separate out the cooperative and competitive effects in the dynamics. Good. So what we can do with the definition of mixed monotonicity is we can construct this very interesting embedding system that has twice as many states as our original system, but has a number of very interesting properties. So the system has states x and x hats. It has an update vector field that will denote with lowercase e. Notice that it doesn't have a disturbance input, so we can think of this as being a truly deterministic system. There's no disturbance input present, and is defined in terms of the decomposition function for the mixed monotone system. So in particular, we're going to make the assumption that we made on the earlier slide, that our disturbance set is a hyperrectangle, W. So W is the disturbance set. That means it has a lower point, a lower corner, and an upper corner. Its lower corner we can write as W underbar, and its upper corner we can write as W overbar. So what we do is to define this embedding system, we evaluate the decomposition function D at the state x and x hats, and then we evaluate it at these extreme disturbance inputs, W underbar and W overbar. That's the update equation for x dot. And then for x hat dot, we swap pairs of variables, but we still evaluate the same decomposition function. So for the embedding system, we'll denote its solutions with capital Phi, and we'll also superscript it with E to remind ourselves that it's coming from the embedding system. And again, it has initial conditions that are now pairs of states, x and x hat. And on this particular state space, we'll define a particular partial order, which we call the southeast order. It's an ordering on R2n, and it's defined as follows: a pair x hats is less than or equal to, with respect to the southeast order, to another pair y hats, if and only if the vector x is less than or equal to y, and the vector y hat is less than or equal to x hat. So if you view this in just 2 dimensions, so if x and x hat are each 1 dimensional, and you have a point at the origin, the points that are greater than the origin lie in the southeast quadrant. That's where it gets its name, the southeast order. So the very intriguing property of this particular 2n dimensional embedding system is that it becomes monotone with respect to our original definition of monotonicity with respect to this particular southeast order. So in particular, what that means is if you take 2 2n vectors, A and A prime, that are ordered with respect to the southeast order, and you consider these to be initial conditions for the embedding system, then the trajectories of the embedding system will remain ordered with respect to this special southeast ordering for all time. So I want to highlight a couple references here for historical note. So the first comment I want to make is that I really like this quote from Hal Smith in this paper from about a decade and a half ago, that this embedding system idea, it's repeatedly rediscovered and its implications are often underestimated. I think we're finding that even in our current line of research, where this rather innocuous looking construction leads to lots of interesting properties that we can exploit. And I want to make, for historical connections, this line of reasoning and this particular formulation of the embedding system has most direct connections to, I would say, these 2 papers. The first paper by Enciso, Smith, and Sontag for the continuous time case, and this paper by Smith for the discrete time case. And so it's worth mentioning that most of what I'm talking about today generalizes very naturally to the discrete time case with some mild modifications to handle the change from continuous time to discrete time. Good. So let me talk a little bit about how we can use this embedding system to compute reachable sets for our dynamical system. So what we're going to do is we're going to introduce a little bit of notation. So we'll denote by RF at some time t, given some hyperrectangle of initial conditions with lower corner x underbar and upper corner x overbar. We'll use this notation to be the reachable set for this system. So what that means is it's the set of all possible future states of the system at time t from some initial point x naught under some disturbance input w, assuming that x naught lies within this hyperrectangle x underbar to x overbar, and assuming that a disturbance lies within its disturbance bounds w underbar and w overbar. The main result, the main theorem for this embedding system is that this reachable set for the system has to be contained within a hyperrectangle that's constructed from the embedding system in the following way. So you compute a single trajectory of the embedding system that is initialized at the extreme corners of your initial conditions, x under bar and x over bar. You compute this single trajectory. It's got two end coordinates, and you build a hyperrectangle constructed from the first end coordinates and the last end coordinates of this embedding system trajectory. This hyperrectangle contains the reachable set for your system. And so the power of mixed monotone systems theory comes from the fact that a single trajectory of the deterministic two-end dimensional embedding system provides overapproximations of reachable sets for your original n-dimensional mixed monotone system. And that's the key factor we're going to leverage in our results throughout this talk. So here's just a very simple example just to put some pictures to this idea. Here's a particular vector field that actually generated the figures on the very first slide. You can compute a decomposition function for this system. You can verify that this particular decomposition function satisfies the properties that we needed on the original slide, and it's also a continuous decomposition function. And so if we consider a set of initial conditions, say here in orange, and we computed the actual reachable sets for this system, we would get this dark blue region over here. If we computed a trajectory of the embedding space for this system, we would obtain an overapproximation given by this outer bounding lightly shaded blue region here. So on the right, it's the exact same figure, except for now we're plotting it in the embedding space. This is a four-dimensional embedding space, so I'm just projecting to the x1 hat and the x1 variables. And what you can see here is that the particular point corresponding to the initial hyperrectangle evolves underneath the embedding dynamics to a point that defines this overapproximating hyperrectangle. So this is the picture, basically, that is the theorem from the previous slide. So as I've been alluding to, this embedding system has lots of intriguing properties. It has interesting properties both in the case when there is no disturbance input, W, and in the case when there is a disturbance input, W. So for example, when there's no disturbance, W, it turns out that the upper and lower triangles of this embedding system, so if I think of the embedding system as in this abstract X versus X hat space, there's a symmetric relationship in the definition. The diagonal, so if you think of all points where X is equal to X hat, this is an invariant subspace of the system. It actually is the original dynamics for your original system. And using properties of monotone systems theory, you could, for example, prove global stability for equilibrium points of your original dynamics by looking at this two-end dimensional embedding system. Today, we're going to focus on properties that we get when we do introduce these disturbances. It changes these properties for the embedding system a bit. In particular, it renders this upper triangular region. So this is the set of points where X hat is greater than X. It renders this set of points invariant for the dynamics. And if there are equilibria that exist in this upper triangular region, those equilibria and the stability properties of those equilibria, or possibly even periodic orbits, give rise to robustly invariant sets and attractive sets for our system. So in particular, here's the theorem. If you can find an equilibrium point, say X equilibrium and X hat equilibrium that exists in this upper triangular region, then the hyperrectangle that's defined by these 2 points, X equilibrium and X hat equilibrium, is robustly forward invariant for the original mixed monotone system. So robustly forward invariant means that the reachable set from this hyperrectangle is always contained within the hyperrectangle for any time horizon t. Moreover, if this equilibrium is asymptotically stable and the basin of attraction includes the entire upper triangle, then this robustly forward invariant region is also globally attractive. Every trajectory converges to this robustly invariant region. And in fact, this is a corollary of a slightly more general result that actually characterizes successively tighter robustly forward invariant sets by looking at rectangles corresponding to trajectories that converge to these equilibria. And this is a result we published last year at CDC. So here's an example, a different system. This system does indeed have disturbance input W, and you can compute, for example, via numeric simulation, that the embedding system for this mixed monotone system, and I've omitted the decomposition function just due to space constraints, it does indeed have an equilibrium. That equilibrium is approximately equal to numerically these points here. And if I were to actually compute simulations for this system, I could get an approximation, a numerical approximation of the true smallest forward invariant, robustly forward invariant set. That's the darkly shaded region here. And indeed, the hyperrectangle defined by this equilibrium point contains this robustly forward invariant region as shown in this figure. Here's another example. This is the particular instantiation of the generalized Lotka-Volterra model from the previous, where the talk began. This particular two species system has a decomposition function constructed as we suggested several slides ago, as shown here. It's again straightforward to verify via numeric simulation. This system has an equilibrium point. Its equilibrium point has a basin of attraction that includes not quite the entire upper triangle, but a large portion of the upper triangle. And what we can conclude is that this equilibrium point defines a rectangle that is robustly forward invariant for these dynamics. And in fact, we've even been able to kind of cook up these strange examples where you can actually find periodic orbits that lie in the upper triangular region. And if you can find a periodic orbit in the upper triangular region, what you end up obtaining is a periodic orbit that is robustly forward invariant. So this is, for example, shows the actual numerically computed reachable set of the system over time versus an overapproximation of this system over time. And we had to get, it took a little bit of care to construct this example, but such examples do indeed exist. As you can basically see, the first two states are being driven by a harmonic oscillator, which are in the second two states, and then the disturbance only lives within the first two states. But again, this is just an interesting property that we can see in these types of systems. Here's an application or example where we can apply some of this theory. This is, I won't go into the details of this extension, but this is an extension we just submitted to CDC 2021. One could also imagine, instead of having a disturbance input that's simply bounded by a hyperrectangle, perhaps this disturbance input is state dependent. So in this particular example, we consider a 6-dimensional planar multirotor, so 3 degrees of freedom. It's a planar approximation of, say, a quadrotor example, where it has a horizontal position y, vertical position z, roll angle theta, and it has 2 control inputs: the thrust through the center of mass in the direction that the multirotor is facing, and it has an angular momentum u2, so that theta dot double dot is equal to u2. And then we can imagine this multirotor, for example, flying in an unknown wind field. So there's a presence of wind that affects both the horizontal and vertical acceleration. And for this particular example, we can assume that this unknown wind component is a function of just the altitude. So what one could imagine doing is attempting to model this unknown wind disturbance as a Gaussian process. The Gaussian process will provide upper and lower high probability bounds on the possible wind disturbance for any hyperrectangle of states that constitute the system state. And so, for example, you can imagine a target control objective where one is trying to reach a target altitude of, say, z equal to 50 while remaining within some safe horizontal bound. And I can just show the simulation results. So in this picture, in this upper 2 plots, these are, for example, the Gaussian process high probability estimates on the wind component. So in this case, we have low confidence in the wind speed. You can see that by these large envelopes. That means that our disturbance input is, we model as being quite large because we don't have a good sense of what the wind speed is. And if we simulate this system, that lack of certainty about the wind speed causes us to have very large reachable sets that cause our system and the reachable set to both reach these unsafe regions. So these unsafe regions are to the left and to the right, and we reach the target altitude, but we can't come back to ground safely because of this unknown wind component. On the other hand, if we were to, for example, collect wind measurements and then obtain a much higher estimate of the wind speed, a much more accurate estimate of the wind speed up until about our target altitude, we could much more carefully provide a feed-forward control that compensates for this wind estimates, and our uncertainty in the wind grows much more slowly over the trajectory of the system, and we can compute reachable sets, for example, a priori, that guarantee that, assuming the true wind lies within these high confidence bounds, that our system will indeed stay safe in this particular example. Good. So some open questions remain. So one question is, how does one go about computing these decomposition functions? Recall that the definition of mixed monotonicity required the existence of a decomposition function. So a rather simple, sufficient condition for obtaining decomposition functions is if the Jacobian matrices, partial f of x, and excuse me, this should be partial f with respect to w. That's a typo that I need to fix. If these matrices are sign stable, so that their entries don't change sign over the state space. You can also extend this, and in fact, Nejmi Ayoze and collaborators did this a couple years ago. You can extend this approach to systems with bounded Jacobian matrices. So this is one approach to obtaining decomposition functions. Other approaches are generally from physically inspired decomposition functions that use domain knowledge. There's been recent work focused on obtaining tightest decomposition functions in algorithmic methods for obtaining decomposition functions. This is a theorem we recently published last year in LCSS, where we proved, in fact, that any system is mixed, any continuous time system is mixed monotone with respect to a decomposition function that is defined according to this optimization problem. And what this optimization problem essentially does is it computes the worst case, both in the minimum and the maximum possible vector field over a set, over the hyperrectangle set corresponding to the entries of this decomposition function. And not only is this a decomposition function for the system, it's the tightest decomposition function. This is directly analogous to the discrete time results that, again, Nejmi Ayoze and Liren Yang published a year prior in CDC. We reframed the problem in continuous time. And what's also interesting is that for some classes of systems, it's actually possible to show and find in closed form the tightest decomposition function for the system. So for example, in this, if we return back to the dynamics that we considered earlier, the decomposition function that we obtained was in fact the tightest decomposition function, and it results in much tighter reachable set approximations than, for example, if you were over approximating based on Jacobian bounds, the bounds in the Jacobian entry. So it can be well worth the effort in finding these tighter decomposition functions that don't come from the Jacobian bounds, as we can see in this example. Good. So I think maybe I have maybe 5 or 10 more minutes. Am I computing correctly? So I want to now turn a little bit to our applications that we've been applying these ideas in. So we've been using these ideas for runtime safety, so embedding safety in the control loop. So let me try to explain the philosophy a little bit and then explain the mechanics we're using to make this work. So the philosophy is rather straightforward. We're trying to take a dynamical system that might be controlled by some unverified controller, and we want to protect it with a backup controller that is capable of rendering the system safe. So we have a safe region, and this is a conservative safe region. So the system's allowed to go beyond the safe region, but it can't intersect, say, some unsafe states. And we want our backup controller to always be able to provably recover and reach this conservative safe region over in some finite amount of time. So our goal, again, is to let the system evolve between this small safe region, but do so in a way that keeps us close enough that we can return to it. What we do in this line of work is we use mixed monotonicity to compute the future reachable sets for the system, and then we ensure that these reachable sets eventually are capable of reaching the safe set, and we use barrier functions and quadratic programming to make that work. So let me give a very brief introduction to this theory of control barrier functions, which has found a lot of interesting use in the controls community lately. So if you have a control affine system, Now, this particular instantiation, we don't have a disturbance input, but we do have a control input U, and it's affine in the control input. And suppose you have a safe set, calligraphic C, that is defined as the super level set of some function H. If one chooses your input U such that the time derivative of this so-called barrier function H is always lower bounded by some particular function with some certain properties, what this control barrier function theory tells us is that the system will remain safe. So what properties do we need on this lower bounding function? We simply need this alpha function to be 0 at 0. This is actually in Lipschitz. These are actually the only two conditions we need. In this case, H is called a control barrier function. And the intuition is rather simple. The idea is that if I have a state trajectory x of t, and I never want it to leave this set C, which is shown here in this figure, what I do is I make sure that the speed with which this trajectory is approaching the boundary of the safe sets, or the set defined by the super level set of H, I make sure that this speed is slowing down as I approach the boundary. That's captured by this lower bound, which is shrinking as I get closer to the boundary. The reason control barrier functions are quite useful is that this constraint here, with the asterisk, is actually affine in the control input U, which means that for a particular state X, I can efficiently online compute a control action that satisfies this constraint. And there's some intuition here that barriers strengthen the usual invariance condition where you need the vector field along the boundary to point inside. What we do here is we actually require the vector field even on interior points. They have to point, they can't point too far outside. And basically, we make sure that the direction that they point doesn't push it to the edge of the unsafe set too quickly. Good. Okay, so a basic problem with control barrier functions is that the safe region that you have might be rather conservative. It can usually be rather difficult to compute a priori offline the least conservative safe set for your system. So you might, for example, linearize your dynamics, compute a conservative safe set based on the linearization. And then what you want to do is you want to make sure that some backup control policy is always able to eventually reach this conservative region. So here in this case, the conservative region is in green. This orange region we don't know explicitly, but we want to check that for all points within this known region, if I apply a backup policy, I'll eventually reach the conservative region. Now, if we go back to the realm where we consider a disturbance input, it's not sufficient just to compute a single trajectory for the system. We need to compute an entire reachable set from a particular point. So in this case, we're computing this reachable set as a hyperrectangle, and we want to make sure that this hyperrectangle is always contained within this set, this green set here. So what we'll do is we can define what I'm calling here H tilde. This will be the sort of the best case scenario for our safety computed along the reachable sets of the backup dynamics. So if I use phi backup to denote, again, this state update map for the system under the backup controller, and I look at the best case evaluation of this function H defining our conservative region, and I declare this to be H tilde will be positive whenever my system eventually reaches this conservative safe green region. So we can now use this new H tilde as a barrier function, which we compute implicitly. We never actually explicitly compute it. We compute it using this maximum formulation. And we can use it as a barrier function provided that, because if you recall the barrier function formulation, we need to compute the partial derivative of this function with respect to x. So we can use it by the chain rule so long as we can compute the sensitivity matrix of the backup trajectory to x. And again, the difficulty comes if we want to include uncertainty. So we have to make a slight modification to include uncertainty. What we have to do is we actually have to look at the sort of our best case in time, worst case in reachable points evaluation of this green region over the reachable set, which in this case is shown as a rectangle. So we can write this in this compact formula here, where we define a function H tilde, which is the maximum over some time horizon capital T of the infimum of this conservative function h evaluated over all points in the backup reachable set for the system. Good. And a couple points, technical points to note. If you assume that h is concave, then you can replace this infimum with a minimum over the corners of the reachable sets, which makes it a finite number of computations. And then instead of this minimum over a finite number of corners, you can replace it with a soft min differentiable approximation, which provides a conservative under approximation of this sets, and you can make that conservatism arbitrarily small. And we can compute the gradients of this conservative soft min approximation numerically by computing the sensitivity of the embedding system. So these are sort of the three computational ingredients that makes this approach tractable. So let me just show two examples. The first is an academic example where we consider a 5-state system. This system has 3 vehicles or 3 carts moving in a platoon. So there's the states are the velocities of the 3 vehicles and the displacements between the 2 pairs of vehicles. We assume a backup controller, which just applies a nonlinear spring force to the 2 carts. And we just declare safety so long as the relative displacement between the carts stays less than or equal to 8 in this particular case. And what we do is we can compute a conservative invariant ellipsoid by linearizing the dynamics. So the backup dynamics are nonlinear because of this nonlinear spring force. We linearize the dynamics. We compute a linear Lyapunov function, say for the as an approximation for the nonlinear dynamics. This Lyapunov function is valid within a neighborhood of the equilibrium points, and we use that to create, in this case, this ellipsoid here. And then what we do is for any controller that's suggested besides this nonlinear backup spring force, we just ensure that this nonlinear backup spring force brings the vehicles back to a safe distance. So here's the video. So what's happening here is this is the trajectory of the system. We're computing the reachable set that's shown in the lightly colored trajectory and in the rectangle here. And we just make sure that this reachable set is always contained within the green ellipsoid here. And the red trajectory is some other proposed controller, right? But this proposed controller would force the system beyond this conservative safe region. So this control barrier function comes into play and keeps the system within reach of this conservative safe region. So that's one example. So the other example I want to highlight is this 2 planar multi-rotor example. So we assume we have the same multi-rotor example we solved several slides ago. We just now assume we have 2 copies of these of this system. So the overall system has 10 state dimensions. That's because each of the multi-rotors has 6 state dimensions, but then we replace, instead of having 4 positions, we replace it with 2 displacements because we're only interested in the displacement between the vehicles. So we end up with 10 state variables total. We introduce disturbances in the acceleration. So we have a 6-dimensional disturbance vector, and we define safety to be some ball around a nominal displacement, and the displacement is given by the delta y and delta z variables. So one interesting thing to note about this planar multi-rotor system is that if you were to compute, say, using, if you recall your nonlinear control theory, if you were to compute, if you were to try to feedback linearize the system or compute the relative degree for the system, the system generally doesn't have a well-defined relative degree, which means that in general, and it depends on this particular control barrier function that's proposed, but in general, the classic control barrier function paradigm won't apply here. So you can't just apply a standard CBF given the ball around the nominal displacement, because there are some points on the edge of that safe set where your control action doesn't affect the dynamics in the direction that you need it to. So the message here is that the standard CBF approach doesn't work. And instead, what we're going to do is we're going to apply our proposed method where we look ahead on the dynamics and make sure we stay within some conservative safe region. So what we're going to do in this example, and what's really interesting about this example, is we were able to implement it on hardware. So it's a hardware in the loop experiment. We implemented in C++ on a Jetson Nano single board computer, which would be like the type of computer you would actually put on one of these quad rotors. We use a Gazebo for the physics engine. with a PX4 autopilot software stack, and we use for a particular quadrotor, we use this 3DR iris multi-rotor. So we're doing this in Gazebo, we're doing this in the full 3 dimensions for each of the multi-rotors, but our control algorithm is just working in this kind of planar multi-rotor paradigm, and we use ROS for the communication between the controller and Gazebo. So here's the figures that come from this simulation. So as we can see that we have a conservative safe region in green, our overall safe region is purple, and our basic approach lets us, in black, lets us leave the safe region in green so long as the reachable sets, which is shown in red, reaches the green region. And this is a zoomed in version where you can see us doing the reachable set computations to ensure that we're within the safe region. So let me show this video, let me show what's happening in this video. So the pair of red UAVs, multi-rotors, this is what happens if we don't apply our safety controller, and you can see they get close and collide. The black multi-rotors are what happens when we apply our safety controller. On the right is an animation of what's happening. So again, the video is not particularly flashy, but what we can see is what's happening is we're avoiding collisions in real time by doing reachable set computations. So what I really want to highlight about this example are in the next few slides. So let me just show some plots, what's happening here. So in these bottom 2 plots, we're showing the thrusts for the 2 multi-rotors. Excuse me, I don't label the which vehicles, but this top plot is for the first quadrotor, the upper one, and the bottom plot is for the lower quadrotor. The blue trajectory shows the desired thrust. The orange trajectory shows our filtered thrust, which keeps us safe. As you can see, for about the first half a second, there is no filtering happening because the systems remain safe even with the proposed thrusts coming from the unsafe controller. But over time, our runtime assurance strategy has to kick in, and it has to modulate the thrusts to keep the UAVs at a safe distance. Remember, it's also looking over a time horizon. In this particular case, it was looking over a time horizon of 5 seconds, and it's computing this best case time over that horizon. In our case, that best case backward looking time was around 4.5 seconds. So what's really impressive, I think, about this example is how quickly we can do these computations. So this is a breakdown of the components that are in this control strategy. We have to compute, we have to simulate the embedding trajectory, which we do again using forward Euler integration coded in the Jetson Nano. On average, this takes about 4 milliseconds to compute. We have to compute this implicit barrier function, which I call this H tilde soft. This takes about 3.5 milliseconds to compute. We have to compute the sensitivity of this function, which requires about an extra 2 milliseconds of computation time. This all gets combined into a control barrier function formulation, which is a quadratic program. This takes a little less than 1 millisecond to solve. And combined, we can do all of these computations in 10 milliseconds, which means that we're running this example on embedded hardware at 100 hertz. And this computation includes a reachable set computation for a 10-dimensional system. So every 10 milliseconds, we're recomputing an overapproximation in the reachable set of a 10-dimensional system that we use to maintain safety of this overall system. So that's what I really want to highlight about this example, is that it's doable. We can implement this very, very quickly on embedded hardware. And so I think there's lots of potential for introducing these ideas into optimization-based control frameworks. So let me just provide a few concluding remarks. So again, in many applications, so formal methods is one. In this talk, we focus on runtime safety. It's the speed of the reachability approximation that's more important than the exactness of these reachability estimates. The theory of mixed monotone systems is a promising approach that produces these rectangular approximations. It naturally incorporates things like disturbances, which is important for these uncertain systems like these multi-rotors or unmodeled dynamics. For example, that multi-rotor, we were modeling it in the plane, but in reality, in the Gazebo simulator, it was in 3 dimensions. And this need for finding decomposition functions is becoming more science than art. So with the recent work and computing these decomposition functions, we have a much better idea of how to compute good decomposition functions quickly. So I want to thank my group. Of course, this work is certainly not possible without them. I want to highlight a lot of what I just talked about is actually quite recent work from our group. So I'm highlighting some of the papers here. that talks about this recent work. This first paper is a tutorial paper, which might be a good reference if you're more interested in these topics. And I really want to thank, in particular, NSF, the late Hisham Behedi, who is a big supporter of this work, and AFOSR, who also sponsored this work as well.
No worries, Professor. So thank you so much for your presentation. It was so inspiring. I think these have a lot of